So we continue the presentation on the British Standard Code for reinforced soils very broadly. So we said there are two things which are make it very specific. One is of course the limit state method design. Other thing is I have mentioned, of course we will continue today, that there are two basic methods which are different. One is called the tieback wedge method, other is called the coherent gravity method. I think today, if time permits, we will be able to go through that also. Then we had also developed this partial material factor safeties, partial material factors, and we discussed in some detail on the partial material factor for geosynthetics. Okay, we will discuss again maybe in the third lecture from now how to deal with that and how to obtain the design strength. Then we have also got partial material factors for soils. This we have seen also. So what exactly is what we are going to do is the soil parameter design value. XD is the water parameter design value, and SK is what you are getting of the value of the parameter. That means whatever you are getting in the testing, those values is characteristic value. Okay, and that you are dividing by FMS. That means partial material factor for soil. S is subscript is for soil. And so what we are going to do every time, these factors are always going to be greater than 1. Naturally, in some cases we divide by 1 and we divide by that factor, or some cases loads we increase. That means it becomes multiplication factor. So in this case, we are decreasing the value, so we are dividing by the partial material factor for soils. Then we have seen this also earlier. We had the one was the parameter for soils. Other is of course the interface friction which we are looking at. One is the pull-out force resistance, and then another one is the sliding resistance. We also seen last time what are the things which are going to do. So this particular first part of it is going to be pull-out kind of thing, and the second portion which you are seeing is going to be for the sliding resistance. So we see that this entire block, let us say, is trying to move away. This is what we are going to do today, and that's one way of looking at it. Other way of looking at it is that there is going to be a movement away. So both ways are going to be looking at it. That means one is movement away from this trial wedge. That means only this particular portion we'll highlight it again when we go to the actual calculations. So it's being pulled out. So that pull out is being tested by in the laboratory. And other way is that the entire thing is sliding. So sliding at the base. So we got two factors. One is partial material factor for you can say soil material factor for pull out. Another one is also for sliding resistance. Then there are different factors we have seen, combinations, and these are partial load factors for soil self weight, and then partial load factor for external dead load, and partial load factor prescribed for external live load. So there are three different kind of things. So that's why this is the value which you are going to get normally, which is disturbing load, and then that is what you are going to multiply with the partial load factor. These factors are always greater than 1. So in this case, the design load is being increased actually. Okay, so for doing this now, we don't have one single way of doing it now. We have seen already the 3 load combinations prescribed now. In the first combination, we said each of these, one is the self weight, another is the sloping surcharge, another is uniform distributed load kind of thing. All of them have got factor of 1.5 only. Of course, for walls and normally for abutments also. And there is other combination wherein we keep these weights, these two, surcharge and the self weight of the reinforced soil block as one only. But this one, away from the so-called failure zone, is taken to 1.5, and also earth pressure, which is trying to give the overturning now, is also going to be taken as 1.5 times. The last combination, of course, we see that there are no increments which are done now. All of them are taken at the whatever value you are going to get, that value is only taken out. So we also seen that it's worth remembering it. Combination A is going to give you actually the maximum reinforcement tension, and also it's also going to give maximum foundation bearing pressure. And in some cases, it's going to also give the requirement of pull-out resistance, but it's not always like that. Usually the combination B is more for pull-out resistance, and definitely the combination B is also for the worst case for sliding along the base now. So we have to do the entire calculations using this combination A, using combination B, and also combination C, which is also going to be checked for everything else. Other than that, more important thing is it's going to be critical for foundation settlement now. So that's how the limit state, serviceable limit state is also going to come in now. So these factors we have in the picture, we have only given small elements actually. This particular one gives you the entire range of loads which are going to be there. This is for walls, and for abutments is also there. Various factors, vertical load and dynamic load, braking load, many things are really done. We are not doing this in India for most of the cases, but when you go to metallic design, I think they will tell you. I mean, we will see how this is going to be arrived at now. You can see factors are also 1.1, and temperature effects are there. So these effects are going to come to prominence in certain cases. We'll see that also. These are abutments. Then the summary of partial factors I showed you last time. So we got load factors, and then we got soil metal factors, we got reinforcement metal factor, then we have the interaction or friction factors, then we have also the factor safety for bearing capacity and sliding ground device. So these are also given. And of course, before that, we also got one more one, the danger for overall safety. That is one thing is there. And then the procedure we started with now, we were unable to see that, but you can see the actual code, we will realize that now. Initially, we are going to what we call a sizing. Then we are going to analyze for extensibility. And after extensibility is done, we are going to select the rubber reinforcement, and then we will see the interstability. So like that, interstability we can do in two different ways. Which one is going to be better? Which one will be used for which particular kind of work or something else? We will see. One is the taper gauge method I mentioned, and second is the core and gravity method. And like this, we proceed actually. And we have to do lots of checks before we come to final design actually. Okay. Now in step one, we said this is actually sizing. What did we say? We said that for a normal typical wall, basically, for a wall, normal retaining wall, plain retain wall, you can say, and the nominal length of the reinforcement which you are going to pick up is going to be 0.7 times the design height. I think you mentioned also, H is not the actual height of the wall, it is a design height. Obviously, if simple wall now, it's going to include the foundation also. And for sloping surcharge, we have seen also, it will involve part of the slope height also. So all of it is going to be, H is considered, H is going to be together. That means part of sloping height and actual height of the wall, and then foundation depth also. All of them are considered in getting the value of H. So 0.7 times H with a minimum value of 3 meters. And then if it is bridge abutment, it's going to 0.6 H plus 0.2 meters or 7 meters, whichever is greater actually. And for other walls, we have got other kind of this one. This is starting point. This is initial sizing. And this is gives you more detail actually. This table gives you more detail, otherwise nothing no specific now. And for all these cases, for trapezoidal wall and other kinds of things, we are going to think of how to design, how to get the initial H. And unless you get the H now, we can't get the trial length also, 0.7 H or whatever it is now. So all of them we have discussed last time. And the next stage, of course, is to go into the actual definition of soil properties. Now, what is the definition now? In the definition, what is it we got? We got, I mentioned again, but it is worth, I mentioned last time, but it is worth noting that we got a foundation soil. We also got a soil which is going to give you the earth pressure actually, for which we have designed the entire thing. And then we got a chosen soil, which you are going to pick up. What you are going to pick up, usually it will be cohesion less soil, that means granular soil. And C is not there, but C could be there in some rare cases. But anyway, it could be having C also, but otherwise this is not done normally. The most common kind of soil which you are going to pick up is going to be granular only. Okay, so then the design height we already got based upon the figures which you got now. And what is it we are trying to do? We are going to draw a line actually, which is arc tan inverse 0.3. I mean tan is 0.3 or arc tan 0.3. So that line starting from the base here, that means from the foundation level, where it's going to meet now for this particular picture, that is going to define the H. So H I mentioned already, it's also foundation plus the regular wall height above the ground level, and then also this part of sloping surcharge by the definition. For each different kind of thing, naturally, these are given in pictures very clearly. Then the main design, of course, this I've shown you in the earlier section actually. What is it we are going to do? We are first going to assume in most cases, particularly for a tieback judgment, exactly like our wedge method of getting earth pressures and design a retaining wall. So what is that method consists of? In this case, remember, we are using a geotextile. We are using a geotextile. So geotextile is initially spread like this. Okay, on the ground level, I mean at the foundation level, let us say, and then the soil is filled up now, and the edge portion now, you tuck it back into this and then compact the soil at the top now. So this is one layer of geosynthetic now. Usually is followed for geotextiles, and then next layer is going to come. We'll see maybe more of it as we go further. So we are going to build up this kind of wall actually in number of layers. And how to design this now? We are first going to draw the wedge. So the active edge is going to be at 45 plus 5 by 2 to the horizontal. So this is the angle and this is the line. So what is the assumption in the theory? Assumption theory is that this wedge we thought is going to move this way. Then only active condition is going to be coming out. So how is it going to come out now? Either it's going to translate, the entire fascia is going to translate or rotate with respect to the base now. Exactly what is done in the normal retaining wall only. So if this wedge is going to come out, attempt to come out now, entire wedge now, that means if this is the failure area, failure zone you can say, then what is resisting it now? First of all, let us see what are the pressures which are going to be caused here on this wall. One is of course the self weight. We have drawn a triangle, it is sand only, and then we got a kind of UDL here, then that is additional load here, additional pressure here now, and then any other loads, level loads and things like that, we are going to draw this much now. Okay, so all of them combined together, we got a total earth pressure diagram. Mind you, in all the cases, we are going to draw earth pressure diagram. We are not actually drawing a total pressure. That means we are not including in this water pressure. We are not including hydrostatic pressure now. It's only earth pressure. So this total cumulative diagram is earth pressure now. And we will see in the further sketches now, if you are going to consider, let us say, an element, which I am going to consider here, from here. Isn't it? So if you are just considering this element only, if you consider spacing, uniform spacing now, you take 50% of the earlier spacing, that means the top spacing, and 50% of the bottom spacing. So it is this zone which is going to give you the earth pressure. So that means we are going to draw the same line actually here, horizontally, and then we are going to take the earth pressure in that zone, which has to be resisted by this particular geotextile or geosynthetic now. So this is the zone, that means this earth pressure which it has to tackle now. So how it is going to tackle now? Is earth pressure going to be converted by enough friction along this entire area? That means area of this is going to be beyond this failure wedge, adjunct wedge now. And mind you, when I say area now, we are getting this line now. We are using 1 running meter across it now. So exactly what we do in normal retaining wall only. So we got this line length here of the effective length. Effective length means the total length is L here of the reinforcement. But then effective length is the length beyond the failure wedge now, which is going to resist this, which is going to resist this. Okay? If this is going to resist it now, naturally, how it is going to happen? It is going to, first of all, it has to be coming from friction as tension now. So first of all, we should see that is the sufficient friction there now mobilized. So we can assume that the friction factor is going to mu, let us say. So mu multiplied by the area of this entire running meter. That means this length multiplied by the 1 meter is going to be the area now. So mu into that area is going to give you what is the friction which is going to generate because of this, because of the interface interaction between this soil and the geosynthetic now. If this is sufficient, that means if this friction is sufficient to transfer the load as tension now, that means sufficient means now it has to be at least equivalent to, or this friction has to be equivalent to or more than this earth pressure actually. So what is the amount of resistance required now? At least this much now, plus a factor of safety. And then if the entire friction, if it is not sufficient, then what we are going to do? We are going to increase the length of this now. Okay, we have to find out enough length, and this we will keep doing from top to bottom anyway. So if enough friction is mobilized to transfer that pressure onto the geosynthetic, now obviously geosynthetic should have enough tensile strength now. So first is friction generation, friction is converted into tension now. So, but the values of that, of course, after factoring is going to be based only on the earth pressure, which is going to take now. That means it's going to depend on spacing and things like that now. So this is typically what we call as a tie-back wedge method. That means this wedge is being tied back into this now. So we will have to analyze actually what is happening at each of these reinforcement levels now. We have to also analyze whether the entire thing is going to fail once or not. And we have to also see not only this line, we have to also draw other lines and find out the wedge stability. That means we are going to talk of the stability at each and every individual layer. We are going to talk of many kinds of failure lines, let us say, hypothetical lines now, we're also going to see actually that maybe this portion is going to slide off. That means from this line, whatever is top portion may slide off also. So we are going to talk of different kind of hypothetical or assumed failure surfaces, failure zones now, and check for each one of them. So we'll keep doing that basically as we keep going. And what did we do before that itself? We said we are going to take it as a what we can call a free body diagram. What is free body now? We already got the height of this entire thing. Okay, we just said there is a trial length required. We said 0.7 h for wall. So 0.7 h is the length of the reinforcement, and across is going to be 1 meter. And this mass is actually acting like a free body, and it may, let us say, slide along the base. It may cause tilting or bearing failure. It may also overturn. Overturn is not always considered by some some theories. So overturn may or may not be there in some of the codes now. So we'll consider these two things now. The third thing is going to be overall slip failure, a global kind of failure, you can say. Okay. So these are three things which are going to be giving us external stability, safety. So for each one of them now, we got a partial factor already. Sliding failure, we got a partial factor of safety. And then overturning, we are not considering. Tilting, bearing pressure, that is a factor of safety. And overall slip also is a factor of safety. So we are going to ensure that the length of this, the trial length we assumed, let us say 0.7 h, is enough to give you stability for each of the partial factors which are going to do, for each of the combinations we said, load combinations which are going to do. Okay, that is first step now. After doing that step now, till this, though these dotted lines are shown, we still don't know what is the length and breadth of this now. What is the what do you call the strength of this required and friction required and things. So we don't know at all. We just said this entire mass is going to. Okay, so that is the initial starting point. After that starting point now, we got the length required for extensivity. Then we are going to look for how the failure is going to occur. We already decided how the failure is going to occur now. With these lengths enough now, then what is it do? What is going to happen now? Our failure is going to be, we'll just go back to the earlier sketch now. We assume that it is a straight line actually. In the initial cases, we are assuming this Rankine theory only. But then later theory shows that this may not be straight line. Actually, this line is not going to be simply 45 plus 5 by 2, not 45 by 2. It may start plus 45 plus 5 by 2, but then it may be reaching the top in a particular direction. So that is what we will see in the coordinate gravity method, but this is just illustrate that only. So any point is that this wedge is going to come out now. So one is it can fail, it may break into pieces near the wedge now. That's the maximum tensile stress. Otherwise, it may also slip. It is simply sliding actually. So we are going to require now the air pressure we already got now. So for that, we are going to see that the tension is sufficient. We are going to see that the length beyond this failure zone also sufficient to transfer the load as friction. So both of them we are going to examine simultaneously with all factors included now. So we'll go back to the code itself now. Again, BS 8006. So what is it they have done now? As I said, they are only considering the bearing and tilt failure, bearing capacity and tilt failure. So this is the bearing and tilt failure. And then forward sliding we are going to consider. The picture makes it obvious. Then, if you are doing hilly regions now, it's quite possible that, and also depending upon the kind of soil we got now. So merely placement, this is tilt means you can say tilt is a function of settlement only, but here the whole thing is moving now. Okay, that's called global or overall failure actually. So we call overall, rotational, global slip surface. For this also there is a factor of safety which are going to give partial factor of safety. And so there are three things which are going to be doing Western stability after initial sizing. The initial sizing we already got the depth of the foundation, also we know depth of the foundation now. The one thing which you have to also remember is this is a different typical kind of structure, flexible structure now. And so we can't assume that this entire load, whatever load we are going to have for this wall, is going to be coming out as kind of UDL as bearing pressure. Okay, it is not going to be giving us the bearing pressure, which is kind of UDL at the foundation transfer stage actually. Because this wall is flexible wall, unlike our concrete wall, unlike our brick wall, unlike our gravity wall. So there are many theories which are really done. But before that, what was obtained actually is that the bearing pressure diagram is something like this. That means bearing pressure seems to be quite high near the face, and then minimum, let us say, near the edge of this end of the wall actually. That means rear end of the reinforcement. In the front of the reinforcement, it is almost quite high, and then it is like this. Now it is very difficult for us to consider. So there have been 5 different ways of doing it now. And a suggestion by Meyerhoff is taken actually. So Meyerhoff said now, you find out the center of gravity of this entire load, whatever loads you have got now, and then naturally center of gravity you are getting, and then we also draw a center line of that now. So naturally between center of gravity and center line now, the what do you call the eccentricity is going to be E is defined like this now. If E is eccentricity from center of gravity to center line of this center structure, this assumed structure, which is a free body as I told you, and what more actually we require? We also had to require actually what is the kind of soil we are going to use. We have to pick up a soil. Initially, we said it's going to be granular soil, and we have to find out the MDD further now. So what we know is the MDD and of course the angular friction, all those details we will have. And right now for the weight part of it now, the W which you are going to consider is going to be given by the MDD and the size itself. Size will be this assumed width initially, trial width, or whatever we got from the extensibility, which are going to get now. And also we are going to multiply that by 1 meter, running meter actually. So now we got the center line of the structure itself, we got the center line of the action of load, vertical load now. And with these things now, we are assuming that the load actually is not being transferred entire width. It's only being transferred uniformly across an effective width, which is equivalent to whatever is the length of reinforcement minus twice the eccentricity. Okay, this will be twice eccentricity. So that is the bearing pressure which you are going to have now. So what is it you are finding actually? You are finding that though this load is really UDL directly, the actual pressure which you are going to get, that for which you have to compete with respect to bearing capacity, is going to be given by this diagram now. Okay, that means the total load is distributed not in the entire length of L, it's distributed only between L minus 2E, which is equivalent to 2E means twice eccentricity, which means this B width only. So that is what we are going to do for bearing and tilt failure. And what is QR now? QR obviously the factored bearing pressure acting on the base of the soil. That is what we are going to see this. This is the factored bearing pressure. And then gamma dm, we know the very well what is gamma, what is dm is the depth of the embedment depth now. And Q ultimate by FMS, the meter factor. So Q ultimate bearing capacity, ultimate bearing capacity divided by the factor of 25 bearing capacity. So that is going to be QR, the factored bearing pressure acting on the base of the wall is going to be, has to be less than or equal to this much. So that is what is going to happen, wherein the QR value is going to be is equal to RV is the vertical load divided by L minus 2E. So that is how we are going to think of it. So our equation is going to be RV over L minus 2E is going to be less than or equal to gamma dm, that means surcharge, plus Q ultimate by FMS. So this factor is what we are going to get actually. So in the same way, we keep analyzing like this, and for sliding around the base also. The entire thing is sliding around the base now. So for this now, we are going to consider two things now, the long-term stability and short-term stability. Short-term stability, of course, becomes critical only when you got cohesion. That means a C5 soil, otherwise we are not going to work about short-term stability. So the long-term stability means obviously in this case sand only. Okay, and C also is there. If you whenever we got a little bit of C, and then we are going to think of soil to soil contact or reinforcement soil contact, any one of them now. That means soil to soil is weak, now naturally it will fail like this, or reinforcement soil contact is going to be weak, naturally that's going to fail. We always remember that soil to soil contact is always phi, is it not? Angular friction phi, whereas reinforcement soil contact is going to be defined by the angle delta. The one thing which is going to happen is, if you are using a geotextile, there are two contact surfaces because there is a geotextile and then there is a soil at the top and the soil at the bottom now. So interactions happening at the base, at the bottom of the geosynthetic also, and also at the top of the geosynthetic now. If it's geotextile, that means it's a twice friction angle. In the other case, we are going to have a grid. So grid means natural interlocking is going to help us now. So that in the case of grid now, the interest factors are going to consider be single only because it's considered the interaction between the aggregate or fill material and the geogrid now. So for geotextiles, which are sheet-like material, it is going to be two surfaces at the top and bottom of geosynthetic geotextile, and if it is going to be a grid kind of thing, it will be different. Also strip also means a smooth strip basically. I mean straight strip now, no holes in that, no openings in that now. So again on the top and the bottom now. So we have to see that's how the definitions are made now. And if you really see the long-term stability, first portion now, there are so many components. So we find that RH, obviously, what is RH now? RH is going to be factored horizontal disturbing force. Okay, what is factored disturbing force? The factoring is coming up because of the load combination A, B, C. So it's called factored. Okay, FS is obviously the material factor of safety. The force factor of safety. What is FS now? Partial factor acting in a sliding now. Okay, so this is how we are going to define for two things now, for both the peak angle and for the rainbow angle. And the second case is going to be for short-term stability. Short-term stability means instead of C prime earlier, we are going to use CU now. You can get hold of these equations and then study these equations quite clearly later. So long-term stability means we are using the effective angles of friction, effective angle of cohesion, effective cohesion intercept. Okay, and relevant factors for that now. And if it is going to be short-term stability, if there is a little bit of clay in that now, naturally we are going to use the undrained strength, undrained cohesion value in both soil-to-soil contact and also rainfall soil contact now. We are not going to much bother about these values when we short-term stability because we do have essentially a sandy kind of soil. But anyway, the provision is there. So after having done this now, we can also look at the settlement now. One was bearing capacity we considered. What did we other consider? We considered also the sliding along the base now. The second thing we are going to do, the third thing we are going to do is settlement now. Now settlement can be occurring naturally due to the settlement of the base. This is settling. The base is settling. That means foundation settling. And also our fill material, as you keep compacting from top to bottom now, also will compress instantaneously. Maybe if it has got high clay, it's going to settle more also. So we are going to talk of the settlement of the reinforced soil zone, reinforced fill zone, and also the foundation actually. These are the two things that are going to be there. But then, because our distribution pressure is not going to be uniform, so there is likely to be a different settlement across the wall itself, and also along the length of the wall if it's going to be a bridge approach. In a bridge approach, the height of the wall is going to change actually. So when the larger height, obviously the settlement is going to be more. Okay, and so between that and let us say the next few running meters is going to be different now. So both across and along there will be different settlements which one has to take care of now. So this is done actually indirectly, partially. So typical vertical moment capacities required for facing systems to cope with the vertical internal settlement of the reinforced soil. Vertical internal settlement. That means we're not talking about the foundation, we're talking about the settlement within the wall now. So if there are going to be discrete concrete panels, okay, so the joint closure will be 1 in 150 relative to panel height. Okay, the closure between the two panels is going to be allowed to be 1 in 150. Now, how we are going to we place EPDM kind of rubber, you can say, between the panels now. So that may compress 1 in 150. Okay, that means if the size of vertical height of this 150 centimeters, it should be able to have facility to settle at least by 1 centimeter. That is 1 in 150. If you got full height panels and block walls, then the required vertical moment capacity of connections increases wall height. Obviously, it's going to increase wall height, and that is left to the designer actually. They are not specifying it clearly. Now, semi-elliptical facings. What is semi-elliptical facing now? In the early days, there used to be also metallic facings also, which is not really done today. So we'll skip that now. Then we already said that the geotextile wraparound facings. No specific limit is mentioned. Very important because they're so flexible. No specific limit except for appearance or serviceability considerations. And later I will show a case history wherein inside rubber settlement moment is there, but we covered it externally so that this is not seen. Whatever is happening within the wall is not seen externally because we had a kind of false fascia on that now. So that is why this geotextile also is preferred because we are not putting any limits on the settlement of the panels. Then overall effect of the settlement also they indicate. One, of course, is that if the different settlement is going to be 1 in 1,000, not normally significant. 1 in 200, full height panels could be affected by joint closing or opening. 1 in 100 is normal safe limit without special measures for discrete concrete panel facings. And then we are not considering the semi-elliptical now. 1 in less than 50 for discrete panels may suffer closed joints if special measures not included. So soft facings may suffer distortion affecting their weighting ability. So individual panels, discrete panels may suffer closed joint. That means the joint is going to overcome another one now. So that means concrete there may get crushed. So that is why we should not allow less than 1 in 50. It's going to be difficult actually. It should be always 1 in 50 or more, 1 in 50 or 1 in 100 or 1 in 200, that's okay. But less than 1 in 50 is not going to be really good actually. So this is a guide only. They are not giving limit. So the authority engineer, in this case, a client has to give a actual value. It depends upon the importance structure, where it's located, and criticality and things like this. Then there are also construction tolerances. Now we wanted this 10 to 15, 20, 30 meter high wall actually. In the same plane from top to bottom. It never happens because construction difficulties always will there now. So maybe one panel is going to move slightly this way, another panel is slightly this way, maybe like this slightly. So that tolerance, location of plane of structure, plane of the fascia which are going to consider, that could be plus minus 50 mm. That means maximum 100 millimeters you can allow this way or that way. That is the total. Verticality, plus minus 5 millimeters per meter height. Okay. Bulging means in the plan like this is bulging, and 25 millimeters in 4 meter template now, plus or minus 25 millimeters. Verticality means when we are taking the along the length of the wall, along the height of the wall now. Bulging means outside. Okay, verticality also is called bowing. It's like this, like a bow. You know, Ramji does the bowing. So that is a bow actually. Bulging means in the plan actually. That means bowing means in the vertical plane, and bulging means in the horizontal plane. So these are the guidances. Now these are construction tolerances commonly achieved for face of retaining walls abutments now. So if by any chance we are not able to construct like this now, most consultants, including me, suggest that we rebuild the wall because our fascia is intact now, our roof is intact now. Only we had to remove it and we had to say recompact the soil, and with this now it's going to be safe. Obviously, if it is going to be more movement now, then a lot of things we have to do to keep it stable. We'll see that maybe one class will have only on the distress of the walls now. Then we are talking about the global stability. So earlier in the sketch I have shown you, global stability meant the wall, of course, is tilting. Global stability is there now. But in this case, we have to do more than that actually. See, one kind of failure, one kind of global this situation we are going to get is like this. That means it's failing like any other wall. Okay, now if the soil here at the bottom is rigid or more stiff now, actually this is horizontal plane now. It's not really giving elliptic or log square or something like that. That's one thing is there. The other thing is that now this wall itself is partly moving, partly rotating now. Now so far so good. But what may also happen is that the failed surface may go within the wall also. So that means the typical failed surfaces, potential slip surfaces can be away from the wall or can be also along, across the wall itself. So these are two things now. Slip surface passing through the structure if the length is going to be less than h. So we should be quite this part is less. This kind of edge will occur when length is going to be less than height. In this case, if length is going to be more, actually, this length is going to be more. This kind of edge can occur now. So we have to really see all of them now. So then we said, after that initial things are done now. So what is it we have done now? We have done the bearing pressure. That means indirect bearing capacity. We said lateral sliding, and we said the global stability, overall stability. These are the things which are considered now. So whenever the actual values calculated is going to be less than the factor which is required, what is it we do? We increase the length of the reinforcement. So minimum we prescribed already. So for example, if it is a 10 meter high wall now, minimum was 7 meters, but on some base sliding, if it is poor material, maybe it requires 1 more meter, 8 meters is the length of the reinforcement. So this is the 8 meters is what is now coming out of the external stability now. Okay, so this we have decided. Next thing is now we have to assume actually that what kind of geometry we are going to use, because we never bother about the actual earth pressure with what is happening, what is the effect of this inside. I explained to you, of course, before the VS code, what is happening. But in the code, we never discuss as of now what is spacing required and how do you get the tension required and also the effective length for transfer of friction as tension. So when you look into that now, first of all, what comes to your mind is what is the likely spacing? Now, supposing spacing can be say 15 centimeters some place, 25 in some place, 37.5 some other place. No, it can't be, because when you're doing the field work now, our soil is compacted regular intervals, regular thicknesses, regular depths. What do you mean by this now? By and large in India now, our compacting thickness is going to be 200 millimeters. That means it will be usually loose laid at 250 or 270 millimeters, and then after rolling now it comes to 200 millimeters. If you ask him to compact 300 millimeters, it is going to extra work now. So our spacing of the reinforcement we are going to assume will be in multiples of 200 millimeters. That means it will be 200 or 400 or 600, 800 like that only. Now, what is the maximum spacing you can think of? Can you go beyond 8 millimeters? Well, some people have gone beyond also up to 1 meter, but I think 800 is the limit which normally we have to impose. Why? Because I told you the homogeneity is lost actually. Because the space material reinforcement is so vast basically that it's difficult to imagine that it's behaving like a composite specimen actually, composite system. So that's why the limit is placed, such that the entire mobility, entire stability is going to be considered seriously. So in trying to do that now, interstability we consider at each level now. So I'm considering this, let us say, at a depth of Hj. Okay, the Hj, and this is what I'm considering at Hj. So I am trying to draw the portion of Hj and whatever above. That means I'm considering only the stability of this entire thing above. But then what we are trying to do, what is happening to that particular reinforcement which is described here now? This reinforcement describing is this. So what is affecting its behavior? Only the portion of the wall above this only. That's why this is shown here now. So as far as this reinforcement I have shown here is concerned, okay, what is the bearing pressure now? Again, we calculate the length is there now. We have to find out the center of gravity of this now and find out eccentricity. So the actual length minus twice eccentricity is the effective length now. So bearing pressure is going to act upon this effective length. That is one thing is there. Then the earth pressure, what we are going to think of, normally it's Rankine theory. When you go to other method, like coherent gravity, we'll use Coulomb also. But then in the first case, we are doing Rankine because that's easiest for us to do. So earth pressure distribution, we are deciding like this. This is earth pressure distribution. Okay, next thing we are going to also think of it is, we are going to think of what is the effective reinforcement length. Sorry, this mistake actually. So we'll take it as like this. If this line is going to be 45 plus 5/2, is trial of that. So this entire bridge is expected to fall down. So the effective length beyond this value zone is going to be this length now. So our friction is going to act upon this length only. Okay, so we had subtract from this length whatever is there in the wedge itself. We can calculate very easily, and then multiply by the friction factor. We'll see what is friction factor, and then decide whether this friction is sufficient or not. If friction is not sufficient, naturally we are going to increase the length. We are going to increase the length of the reinforcement. So like this now, we have to keep checking at every level of reinforcement 1, 2, 3, 4, 5, 6, 7, 8. We have to check up each one of them now for all the characteristics of friction now. If friction is sufficient, that means it will transfer the earth pressure as friction. What is the earth pressure now? So area required is going to be, this is reinforcement we thought now. So we are going to take 50% spacing at the top actually, 50% spacing at the bottom. So that is what it actually gives you, SVJ. S is the spacing and vertical spacing is what is mentioned now. There is also horizontal spacing sometimes. Why horizontal spacing will come in now? When you got strips placed at different intervals, naturally horizontal spacing is going to come. Otherwise, the sheet now only SVJ, the spacing is vertical spacing is going to come. And what else is going to be there now? The entire, what you call geotextile is going to be used basically. It's not in pieces. Okay, and then this is the area, this is command area you can say, and that earth pressure we are going to consider for the safety of this entire thing now using these reasons. So we find out whether the friction is sufficient or not by initially this length assumed from the stability. It's not sufficient, we will increase the length now. So when once you do that, the friction is enough to transfer it as a tension. So the tension value is going to be exactly the factor as pressure. Nothing more than that now. So that is what we try to do. So what is the tension which are going to require now? Tension will be naturally due to three things, which is mentioned here now. The self weight of the and any such vertical strip load and horizontal shear applied load or strip load actually. Okay, and of course we also consider tensile force due to cohesion of the soil because it's negative actually. So we have to consider all of them now. So for friction fill, it will be TPJ plus TSJ plus TFJ. It looks very complicated, but it's very simple. Self weight only, vertical strip load only, or any other horizontal shear also. So all of them are going to give you combined together. TJ is the maximum ultimate limit tensile force TJ to be resisted by jth layer of reinforcement at a depth of Hj from the top. That is very important. Hj means HJ is going to give you what is the vertical stress actually, because we are going to have vertical stress required to find out the friction. That means sigma is vertical stress multiplied by tan delta, let us say, if delta is the angle of inverse friction, and naturally that is what we are going to consider. So if you require only tensile force due to self weight and any surcharge now, again Ka is the coefficient of pressure now, sigma Vj is the vertical stress acting upon that now into SVJ is the spacing now. And what is sigma Vj? Sigma Vj is exactly same thing we decided now, sigma like this now. We are deciding in this area L minus 2E, not the 4 length now. So that is what I said. Whatever is the total vertical load, we are divided by the effective length, let us say, in terms of eccentricity. So that is the sigma Vj. Sigma Vj is the vertical stress now. So everything is known. K is, of course, a function of phi only. SVJ is spacing, which you imagine anyway. So SVJ is chosen once sort of chosen initially. Now we can change it in multiples of 20 millimeters as we thought now. Okay, so that is the equation for self weight, that is TPJ. And then we have similar equation for any strip loading. Now strip loading is different from this now. Suppose this is strip on which load is being applied. Okay, this is strip. Okay, now this load is distributed at an angle with one horizontal into two vertical on both sides. So what is it you will find is that whereas this line is going straight actually, and this line is cut off here now. That means above this now, the effective length is going to be reduced. So that all that is taken care of now. Again, the same thing now, K and coefficient of active pressure multiplied by all these values now, and that is SL is going to give you the actual strip load which is there. FF is a factor for them, factored value, and what is DJ? DJ is going to be the thickness. DJ is sorry, I forgot. DJ is this effective value, this length. Okay, so like this we are going to find out what is the tensile force required due to the vertical strip load, and then also similarly for horizontal shear now. Now horizontal shear is working in a different way because this is a strip which is going to give you width of the strip is again B, and this strip is going to have a horizontal shear load. So that's the way. So if this is a horizontal load, shear load actually, this is distributed again at 45 plus 5 by 2, and the maximum value is the top now, and minimum value at the bottom of this line of 45 plus 5 by 2. So that will be, that means when we are considering, let us say, the second layer here, we are going to consider the pressure here now. If you are going to consider third layer, we are going to consider the pressure here now. So that's why we said we are going to do individually one reinforcement, other reinforcement, starting from top now. So first reinforcement, second reinforcement, third reinforcement, we keep doing from top to bottom, each one of them. So initially we distributed easily because only self-weight and sloping surcharge, and that was only, the only consideration was the Markov distribution. And second one, because of the strip actually, again distributed as 1 into 2, and then the horizontal shear distributed in a different way. So these are the standard ways in which we try to do. And due to cohesion again, the similar way we try to do that. And finally, what we're going to do, this checking up means really in terms of rupture, in terms of adherence. So in terms of rupture means the TJ value has to be less than what is TD? TD is the factor value of the tensile strength. Tensile strength is the factor means from creep and things like that, and then the material factor of safety. So that is what is done actually. And adherence also we can calculate. We already said that adherence value we are going to consider for this. Adherence means what adherence is going to come in now? That is bond or pull out. So friction value we are going to use for pull out for this now. And the earlier case we are using basically the sliding resistance. That means I repeat again. In these cases, what we are going to use now? We are going to use the sliding resistance. In this case now, we are going to use the bond resistance. That means we are considering the beyond this now. So like this is called local stability check now. That means we are going to check up these values one by one like this now. Either it should be failure, rupture, or adherence now. So adherence value has to be also, effective value is going to be more than that of the earth pressure. And same thing is also done in terms of earth pressure, the total rupture or tensile strength now. So these are defined very well, but in the class it's difficult to go through all of them now. TJ is the maximum reinforcement tension obtained for all load combinations, and TD is the long-term design strength of the reinforcement. So that is what I said we will calculate next time. when we have a separate class on this, because we do number of tests. We have to also see what is the life of the structure now. So that value is what we are going to have TD and divided by the factor safety, partial factor safety. And then mu is the friction, we said, friction between the fill and the reinforcing elements. LEJ, I already said, is the length of reinforcement in the resistance zone outside the failure wedge as the jth layer of reinforcement. So first is regarding the tension, second is regarding the friction, we can say that. So this was the simplest method we can think of, the tie-back wedge method, wherein we are actually going to use essential Rankine theory, and also for analysis we are going to use wedge theory. When we want to do further, actually, the other method which are also available is the, what I said is core and gravity method. Core and gravity method differs in two different ways. Why this method has come into picture, we'll also see. One is a flexible kind of geotextile or geogrid now. Another could be metallic reinforcement. So when the wall is trying to take up these loads, actually, in the case of a metallic reinforcement, the movement is not going to much now. When one movement is not going to much now, it is supposed to take care of the earth pressure which is higher than active. See, for active case to be developed now, what should happen? The wall should move by certain distance. Okay, so wall is going to laterally translate or rotate with respect to the base. Whereas in the case of a rigid reinforcement, or what we call as inextensible reinforcement, that is not possible. So what is assumed in this case is that at the top, what is that which you are assuming now normally? So what is it we are going to assume normally? We are going to assume normally in the tie-back wedge method, the earth pressure coefficient is Ka. K value is going to be same from top to bottom of the wall now. In the coherent gravity method, the first thing which you are going to do is that if you consider from top 6 meters only, so at that point and below, the earth pressure coefficient is going to be active earth pressure coefficient, and beyond that, that means from height 0 to from the top from 0 to 6 meters to the bottom now, this is going to be giving you the K naught now. So we interpolate between these two things now. So that is the way in which you are going to take care of the earth pressure is going to be coefficient is going to be different. At the top, it's going to be at rest condition, and 6 meters below, it's going to be active condition Ka. So that is first difference now. And mind you, this for inextensible reinforcement like metals now, and also for complex structures, even that is given here actually. So complex structures are, let us say, number of tiers are there, 3-tier wall now, or on the wall now, there is a kind of big tower kind of thing for you can say electricity transmission, something transmit towers, or when the lengths are going to be so widely varying actually of the reinforcement. So all these critical structures, we are to do the second method also, not the first method alone. The other thing which I also said was that in the tie-back wedge method, what is it trying to do? We are trying to draw this line at 45 plus 5/2. So when once you are trying to draw this line, what is it you find? You find that the effective length available to us is only very small actually at the top. Okay, only at the bottom its full length is available to us now. So you can see that from friction viewpoint, the top of this wall is going to be critical now. The bottom is going to be normally critical in terms of tension. Why? Usually the tension is going to be maximum at the bottom now. So if we analyze by normal conventional tie-back wedge method, similar to normal retaining walls now, the top portions of the wall is critical with respect to the friction, and bottom portion of the wall is critical with respect to the tension now. Okay, and this is happening because we got actually this line as a simple line at 45 plus 5/2 from the bottom, from the foundation level now. But what they observe now is, yeah, this is not going at like a line now, this is actually going in a curved fashion. That means starting at same 40 plus 5/2, like a tie-back wedge method, but actually it is going up in a near vertical fashion. So this active zone now is reduced basically. Resistance zone increase, that means now the effective length is going to be this much now. So you got enough length to take care of it now. Mind you, this length is going to be critical for in two ways now. When you're looking at the length from a tie-back wedge situation now, okay, one is effective length is less now because beyond the active zone we are going to take it now. Other thing which you are going to also consider is that what is sigma value? Sigma value is going to be very small now. So sigma multiplied by tan delta or tan of the friction of the pull out now. Okay, so sigma tan delta is going to be very low here now. Whereas the same values at the bottom is going to be full sigma, that means full weight is going to be there now. So that's why the criticality of the friction is not going to come at the bottom now. It will be always at the top. So sometimes in rare cases, we had forced to put another reinforcement also to give us another face now. Or some cases, we also increase the length of reinforcement at the top. Maybe top two layers will increase and other layers are going to be lower only. So this observed fact, or also by analysis of FEM and all, show that this is not such a line meeting the top at say 40 plus 5/2, but this line failure zone is extending at 1 year vertically. So to do that now, they had a lot of estimates and found out the maximum stress zone. That means, these are all loci of points of maximum stress now, like this. This 1 point of maximum stress, 1 point of maximum stress. That's where the failure line is going through this now. So for that now, they assumed that you consider at point 2H. Okay, draw a line normal 45 to 5/2. So at point 2H width actually, you just draw a vertical line. So from this point, they assume by and large it's going to be near vertical. So only from here to here it is inclined, like in the classical case, and beyond it is going to be different now. So we find that these are the two fundamental differences between the type-by-type method and the coherent gravity method now. And coherent gravity method obviously applies very easily for metallic reinforcement and complex structures. The last step which we are going to do is, earlier we remember we are trying to analyze the stability, internal stability at each layer now. But what is the guarantee that the wedges are not going to fail? So for example, if this is a seating load also, like UDL and things like this now. So what is going to happen now? We find that the failure planes, we can draw a number of them now, starting at any depth now. We can start from the bottom, we can start middle and different kind of things now. So we can draw all possible kind of lines. Obviously, the failure planes can't go through the seating for this strip load or whatever it is now. So beyond that now, we can draw any number of lines, sometimes going out also. In the slope also, we can draw any number of lines. So we are drawing, mind you, at different angles other than 45 plus 5/2, maybe plus 45 minus 5/2 and minus 45 minus 5/2. That means more and less than the conventional angles and at different depths also. So that means we are going to draw all the potential failure planes, okay, and they can also be going beyond this one. So this is how we want to analyze this now. That a typical assumed wedge how is going to fail. So we'll just come back on this. So if I assume like this now, let me say that I am going to draw this line assumed failure, potential failure surface like this now at 45 plus 5/2. So this wedge I am going to think of. Okay. In this wedge, what are things which you know now? What are things which you know now? We know only that tension is going to be horizontal. Okay, that is known now. And what else is known now? If you assume that this angle now, this is the angle at which you assume this angle now. So in that zone, actually, the reaction which is going to act is going to be naturally acting at phi from the normal towards bottom, because active case actually. Okay, you can revise your retaining wall pressures. So the direction of action of this is R. We know that reaction, and then we know the weight of this. Okay, it's acting vertically only. We can calculate by the amount of zone which is there now. And we can now draw two things. One is, of course, we know the weight. We draw the force polygon and then draw a line parallel to this reaction line. That means this normal, for this normal now, we draw this line at 45, at 5. And so draw a line parallel to this now, R. And then, of course, from here, we also draw a horizontal line because the tension is going to be horizontal only. That's where we place now. So we are going to get the value of T now. Okay, so for each assumed potential failure line or slip line, we are going to draw this now. So what is it we are going to do? The resistance provided by the individual layer of reinforced elements should be taken as, we already said, friction and tension. Any one of them is going to fail. And so what is it we are going to do? Starting from one point now, we can draw these potential failure planes in different angles now. So I did the same kind of thing. I found out the tension required for each one of them now. Okay, so I plotted all the angles here, just representation only. So for this failure zone 1, at some angle now, this is the value of tension which I got. And second one, I got this is the value. And third one, this is the value. So maximum is reached at one parallel distance. So this is maximum value. This is tension which is going to be faced critically from a point starting at any given depth now. So this tension is now taken care of by all these reinforcements. This one is there, this one is there, and this one is there, this is there, and this is there, and this is there. In this case now, I don't know, about 7 or 8 of them are going to be part of this zone actually. So these 7 or 8 reinforcements, we know its design strength, tensile strength now. So this design strength has to be exceeding this limit which you are going to get by this analysis now. So this is the interstability we do now also at different depths and different possible ways, and that's how we check up now that the overall tension of the wedge you are going to get now, that should be satisfied by all the individual tension capability of all of the multiple layers actually. Okay, that is how we are going to find out the summation we are going to find out actually, and that sum has to be taken care of by the tension, single tension. That is the way in which it's done now. So the other things are going to be now more or less construction. Earlier we said there is a serviceability limit which you said now. This limit is going to be beyond what happens during construction. But geosynthetic may creep afterwards also, because we are going to say 100, 120 years now. So there are simple ways of calculating it. We will discuss it in a course of time. So there is a possible creep of reinforcement now. And the limit they have placed is going to be, it should not be more than 0.5% of the 0.5% at the different kind of structures. 0.5% strain of the original actually, total strain. Okay. That is 0.5 to 1. Normal walls is 1 and abutment is going to 0.5% now. Very difficult to calculate, but one has methods of calculating this also. And there are a lot of, you can say, different opinions on this now, but this is the only code which gives us these limits actually. And we can also see all these limits happening. And the other thing which is going to left over, if time permits, Dr. Jimmy Thomas will cover later how to design a fascia and things like this now. Fascia can be the concrete blocks, concrete full height concrete panels, or it can be blocks. We'll see all those things later. And it could be also gabions. Okay, so these are the gabions, metal gaskets actually, and then the reinforcement is going to be placed here. So this is the gabion serving as not a gabion wall. Gabions are being placed in positions which are required, but the stability is also going to come from the actual reinforcement. So this is only working at fascia. In fact, one of our students, Prajakta, she calculated the effect of this gravity also, gravitational effect of the gabion also, plus this. So the advantage she had was she has placed actually as a conventional geogrid, or whatever mesh which are you going to use to make gabion is also placed here now. It means construct simple in areas now, and the economy in all the things she calculated. Later I can give reference to a paper. It's a good paper giving a lot of details now. Then of course wraparound fascia. We said we have no limits on these things now. Normally these are used not as a wall but as a slope. We see that also. And the main thing is that these actually are able to bend. They are able to curve as you construct more and more. So settlement is not going to place any additional load on the fascia here now. You know the fascia is the same geotextile or geogrid coming over this now. And this curvature changing is called concertina. It's called concertinating actually. So this is the first kind of walls which are done. But then today we don't make walls like this, we make slopes like this. Okay, the last thing which you have to do, we'll do in 2 minutes now. What is the connection strength between geotextile and the fascia? Now, normally, by theory, we are providing the entire reinforcement, doing all the calculations now, in order to see that the geotextile geosynthetics actually is taking care of the entire earth pressure. If that was so, at the point of connection between the fascia and the reinforcement, there shouldn't be any load at all. That means connection load has to be zero. But a lot of research has gone into, and also field studies, full height panels and prototype walls and things like that were constructed, and they find that is not so. So from design viewpoint now, the connection, let us say from tie-back method, if all facings with movement capacity or movement capacity connections are going to be like this now, the capacity required, the connection capacity required at the top of the wall is going to be 75% of the tensile strength at that level. And if you consider the bottom now, the toe, it has to be 100% of the TJ value here now. If it's a stiff face, something like a full height panel now, both at the top and bottom, we require 100% TJ. That means whatever is the tension here, we provide 100% of the connection also. And it looks actually silly. We are providing a wall to take care of this. But then the construction issues, which we'll discuss a bit later, are going to make us take the connection. And there are many cases in India also where the connections have given us a lot of issues now. If you core and gravity method, where loading system is different now, active air pressure is different, effective air pressure question is different now. So they gave different diagrams for this also. Okay. So that is where things are there. The other thing which you'll consider in maybe next class is going to be, or later, not next class, later when you come to filtration drainage, is that the detailing is going to be very important actually. The detailing is done in such a way that during construction, no water enters the wall. Okay, if water is going to enter the wall and you finish the capping for that now, this water will remain there. If it's going to remain there, we have to take care of the weight also. Bulk unit we take now, not the effective unit weight. The other thing which you have to also consider is, if it is going to be having a slope in such charge, we should also ensure that the water is not going to come again into the wall. Okay, the water has to be taken away from this by using surface chutes and things like this. The last thing which he would like to, the British code will tell us is going to be that the entire wall which are constructing is actually like a drain. Why it is a drain? Because it is a granular soil. Water should not remain there. So when once it is coming across water from the top by any chance, it is supposed to drain out from the up to the bottom. And if you got a bridge approach, naturally both these walls for approaches are considered as a drainage media. And that is why we said it is better to be a granular soil, not a C5 soil. Okay, C5 soils are more common for slopes and things like that. We will see the advantage and disadvantage of doing all the things now. So the importance of our sandy soils or granular soils is that easy to construct, no pore water pressure built up during construction, and of course it allows the drainage to take place such that there is no standing water anywhere left over now. Nevertheless, we do provide some drainage measures as a precaution, particularly during construction. We provide some pipes and things like that. When you go detailing, we'll also see those things. So this, friends, is going to give us a overall view of the procedure step by step for design of a reinforced soil wall, geosync reinforced soil wall, GRSW, and naturally you will have a soft copy of this entire code along with all the PPTs. And probably, as I told you, by tomorrow I will place all the PPTs in your link. Simultaneously in the link already there is a assignment now. So assignment will be based upon this lecture and all the code what you are referring to. And the assignment is a bit more detailed because also you are going to have an Excel sheet, each one of you. I think first read the assignment, and then if you got any doubts, we'll discuss day after tomorrow in the class. Okay.